All right, everybody. This is lesson 7.4 about power forwards in the NBA. Let's have at it. So, what we're really getting at here is looking at all the power forwards in the NBA and kind of saying is like how tall are the power forwards in the NBA? Power forwards are taller than point guards and taller than shooting guards, but they're not quite as tall as centers. So we are going to take a random sample of 5 power forwards. Now, if you're watching this video, you missed class, but I'm just describing what we're going to do in class. So in Schoology, I have the lesson, and then right underneath it, you see that link for the NBA heights for power forwards. If you open this up, this was a year or two old, but this is a list of all the power forwards in the NBA at that time. If you look, and it's a pretty big list, but there were 115 power forwards at that time, and it lists all of their heights in inches. So yeah, we could just add them all up and divide by 115, right, and get the average height of all these players. But we're gonna, as we always do in statistics, try to ask ourselves, well, how could we do this with a sample? So the population has to be all 115 power forwards in the NBA. Try not to shortcut these or cut them down. The more you put here, the better. The sample is 5 randomly selected power forwards. Okay. It says number 2, refer to the handout that has all the heights. Describe the distribution. Let me go back to that. So what did it look like? It's down here in the corner. So there's all the blue dots. Well, to me, that looks very, very normal. So I'll say approximately normal. Remember, we always are kind of hedging, being careful. We never say, yep, it's perfectly normal. We'll say it's approximately normal. And the mean tells me us right there. This is from the applet, 80.087 inches, and the standard deviation is 1.519 inches, okay? Trying to get rid of that. It's not working. Here we go. And I guess the standard deviation would be inches as well. I'm going to make a note here. This is for a single power forward. In other words, for one. If you pick one person, one power forward, on average, they would vary 1.5 inches from 80 inches. Okay. Now, here's what we're going to do in class, and you'll just have to, you'll miss, but you can kind of get the idea. Everyone in class is going to take a random sample of the 5 power forwards from the list. They're going to record their heights, then they're going to add them up and divide by 5. So I have 5 samples here. 81, 82, 81, 80, 78 was the first sample. Add them up, divide by 5, and you would get an X bar. Today we are working with means, sample means. Last week was proportions. Now we're taking numbers that it makes sense to find an average of, an average height. So if you were, you want to follow along, what I would do is I'd get my calculator out, and I would go to math, probability, random integer. There are 115 power forwards, and I would do 5 like this to get my random 5 power forwards. So you can see here, there's my first sample, and I would highlight or mark or whatever those 5. You could put this into Notability as well, right? Get your 5 heights, write them down. add them up, divide by 5. And you're going to do that 3 times. So there's my second sample, and there's my third sample. You want to make sure your samples don't have any repeats, any repeated players. Little side note, this sample is less than 10% of the population. 5 is less than 10% of 115, and that's good, okay? Because that means I am satisfying the independent rule. It's not asking for that in the notes, but it's just good to, I'll make a little note. 5 is less than 10% of the population, which means, arrow, independence is met. All right. And then what we're going to do in class that you can't really replicate is we're going to have every student do this 3 times, and then every student will take these 3 numbers and bring them to the board and put their dots on the board. So, 80.4 would probably, this first one would probably be like right there. 80.8 would be here. 80.2 would be here. So these 3 red dots would be these 3 samples. And then we'll have all these dots. So this is a make-believe distribution of what might happen in one of my classes. We'll probably have more dots than this, because if every student does 3, and I got about 25 students, 25 times 3 is 75. I should have 75 dots, so I should have more than this. So when we put all the dots on the board, we have a sampling distribution of everybody's X bar, okay? So this is just kind of a made-up sampling distribution. They should all kind of look like this. It kind of looks normal, which is the shape, okay? I'd say it's pretty close. It's approximately normal, all right? And the mean, it says estimate it. What do you think the average is? Somewhere in here, maybe? Just kind of, we're just estimating. So I would say maybe it's about 80. And the standard deviation, again, estimated. What I would do is think, okay, if I draw a curve over this, remember most of the data is within 2 standard deviations. So if I went 1, 2, 1, 2, it looks to me, and then here's the middle. So like 82 would be 2 standard deviations up. 81 would be 1 standard deviation up. So I'm going to say the standard deviation is 1. It's an estimate, okay? Now let's get more into the details. So we're going to use the normal distribution to find the probability of taking a random sample of 5 of these power forwards and getting an average, a sample mean, less than 79. So here's your curve. We're going to get more specific, though. We're not just going to estimate these things. To get the actual mean of the X bars, and again, what does this mean? This means average of what? Of the X bars. So the average of all of the samples you could possibly take will eventually equal the mu of the entire population. It will equal the average of the entire population, which we already know. We have that right here. This is the average when you add up all 115 players and divide by 115. So that is what we will get. It will be centered at 80.087 inches, which isn't bad, right? Here's our sampling distribution. It looks like it's pretty much at 80. We're doing well. So my curve is centered at mu, okay? Mu, which is 80.087. Now, the standard deviation, you might be like, oh, well, okay, we grabbed this for the mean. Why don't we just grab this for the standard deviation? Good idea. However, this is the standard deviation for a single person. If you only sampled one person at a time from the list, this would be the standard deviation. We are sampling more than one person. We are sampling 5 people. So we take the standard deviation for a single person and you divide it by not just 5, it's the square root of 5, okay? Maybe I'll keep this more general first, by the square root of n. So this would be, in numbers, 1.519 divided by the square root of 5. I got that 1.519 from right here. Okay, so what is this? Take your calculator out and do that if you need to. This is 0.645 inches. Here's the thought process behind this, folks. If I only grab one person, this is the standard deviation, right? If I increase my sample size, increasing sample size always reduces standard deviation, always. So that's what we're doing here. And we'll get into a little bit more of why throughout the chapter and throughout the whole course. So we divide by the square root of the sample size. So that's the standard deviation of this curve over here. I'll label some of it just to be more thorough. So the center is 80.087, and the standard deviation is 0.645. So that means my first standard deviation above the mean is 80.732. Let's do one more. I always like labeling my curves because it helps me understand really what's going on. So there's 81.377. What if we go the other way from the middle? 80.222. One more standard deviation down. 79.577. Okay. Because this really helps me, and I can pretty much get a pretty good estimate of the answer right now. Let me actually go back to my question now. What's the probability you do this and you get a mean less than 79? Well, look, folks, 79 is even lower than where I'm at. This is 79, way down here, all right? We already know two standard deviation rule, right? We know that between here and here, two standard deviations, this is 95%. Let me do this with an orange. So here to here, I already know this is 95%. Therefore, this chunk that I'm looking at, this right here is 2.5%. And the purple isn't even all of that. So I'm thinking it's less than 2.5%. I'd be guessing like a 2%, okay? Let's get a z-score and see what it actually is exactly. So my z-score is my value of 79 minus my average of 80.087 over my standard deviation of 0.645. That is negative 1.62. You could look it up on your green packet. I'll show you the calculator. Second distribution, normal CDF. Remember, so what I just found here, this keeps going way down here to a z-score of negative 99, and this z-score is negative 1.62. So my lower is negative 99, and my upper is negative 1.62. That's bigger than I thought it was. I wonder if I did some math wrong higher up. So it says it's 5%. So the probability of getting an X bar of less than 79 inches is 0.0526, okay? I gotta chase this down. What did I do wrong? Because I thought it was gonna be less than 2.5%. 1.519 divided by the square root of 5. Oh, there it is, folks. Shoot, I based the whole thing off of, this is slightly wrong. This should be 0.679. Well, here, just for, so these red numbers here up across the bottom are not quite accurate. But I like chasing down the right answer, so I'm going to do it. 0.679. So this one was actually 79.408. And this one more, 0.679 was 79.408 minus 0.6. This one was 78.729. So I guess that makes more sense. It moves my purple line over a little bit, right? This purple line would be like over here, which increases my purple to there. So that does make more sense. My z-score is still correct. It's not quite negative 2 z-scores. All right, there. So I did not update this one or this one, so those are not right, but you could fix those if you so desired. All right, here's the punchline, and then you're done. So we're doing sampling distributions of x bar, meaning adding up the sample and dividing by 5. If it's approximately normal, well, it will be approximately normal when the population it came from is approximately normal. Quick little reminder, here was the population right here. That is very normal. So if I sample from that distribution, then my resulting sampling distribution will also be normal. Pretty logical, okay? Here are the formulas. I did that one right up here. And I did this one right there. And then we are finding a normal curve now. I did this formula right here with the actual numbers, but here it is in its general form. You take your x bar, which is your sample, minus the average of the entire population, and then you divide by the standard deviation of that sample. And again, the standard deviation of that sample is based on or affected by the sample size. All right, see ya.